All right. Hello, everybody. Hope you all are doing well. For those of you who don't know, welcome. Ask us anything about electrochemistry. Let me make sure We're testing out some new software, or at least I'm testing out some new software, Restream, for our uh, Ask Us Anything About Electrochemistry live stream. So bear with me as I'm playing around with this, but I think that this software is pretty powerful, and you'll get to see things. All right, hello everybody, Prahapt and Chris. Hello, good morning or good afternoon, whatever time you're in. As we begin, usually I want to just have my little disclaimers. Welcome to the live stream. The purpose of this live stream is to make sure that we get a lot of questions from people via email, webinars, um, what is it? Email, webinars, phone conversations, just a lot of different questions. And in this live stream, we're going to be trying to answer some of those questions in a little bit more detail. Electrochemistry is a very difficult and challenging subject, and we're just trying to help people who may have some questions and issues with it. So at any time during the live stream, you can ask. Let's see, Chris, for the video is mirrored. Oh, interesting. The video is mirrored. Oh, strange. I'll have to look into that. The video is mirrored. Chris, what do you mean by mirrored? Um, but hopefully that's helpful. Hello, everybody. Let me make sure I'm able to get some of the the disclaimer stuff out. Well, hopefully, my colleague Neil is out today, and so it's only going to be me. I'm Alex, and basically, um, I'll try to answer as many questions as possible. But Neil is the EIS battery expert, but that doesn't mean you can't ask EIS or electrochem or EIS questions or anything of that nature. So with that said, we'll try to stream for as long as we can. Maybe sometimes streams have lasted maybe 2 hours. If there are more questions, I'll try to get to them. If there are less questions, I'll end the stream a little bit early. But this is just an open space for you to ask any and all electrochemistry questions as you want, and I will try my best to do things. Mirrored image, left to right. Posters are backwards. Oh yes, that's right. The posters on the back are backwards. That's an interesting. That's a very good point. But luckily, you don't need to read those weird posters. Yeah, I think that's just my camera right now, but that's okay. As long as you can still read things, what's going on, that should hopefully be helpful. So this will be maybe about 1 or 2 hours. I'm using Restream rather than Zoom. There shouldn't actually be that much of a delay between what I'm saying and when you ask your questions. So I'll be able to answer any questions, any and all questions, or I'll try that you type in. So please feel free to do that. Again, I'll also apologize in advance. We may have a hard time pronouncing people's names when addressing your questions. Lastly, if you're watching this stream after the fact, I will have a description. In the description of this video, you will have a chance to see all the questions that were asked. So we'll put timestamps in it so you can answer these. You can look at whichever question you may have missed, or you want to hear us talk about it again, or hear me talk about it again in this case. So during this time, please ask any and all questions. I am going to um, switch things so you can ask your questions as soon as possible, and I'll try to get to them. However, there are a couple questions that were asked prior to the live stream, so I'll try to answer some of them uh, as I can. So one of the questions was, how can you determine the voltage range of the electrical double layer capacitance? And this was a question the person put it into the chat. Of course, I had to go and delete and add various versions of this video. But basically, during a cyclic voltammetry experiment, how can you determine the voltage range of the electrical double layer capacitance? Okay, so I'm going to try to share my screen and hopefully give you guys an opportunity to hopefully to answer this question. And again, please let me know if you're running into any technical troubleshooting issues or you can't see what's going on. Okay, so let's just first here go. All right, so I just have PowerPoint open. So to address the question about the electrical double layer and what region of the voltammogram it is that corresponds to it, typically what we're talking about, and maybe I'll try to use a slightly thicker marker here. Let me erase this. I'll use the lasso technique. Actually works very well. So now with a thick pen, if we have a voltammogram, and this is the voltage, this is the current, we typically get these voltammograms that look a little bit like this for a single electron transfer process. Okay. Now we know that in this region, kind of highlighted here, maybe yellow doesn't show up too nice, but in this region we have a Faradaic process, right? We have some kind of Faradaic process, but the electrical double layer capacitance is a non-Faradaic process. So where is that happening? Well, it is happening in this region, but we would typically look in the region where there's no Faradaic process here to determine the electrical double layer capacitance or the voltage range. And really you have to do a CV to get this kind of information. And if we blow this up, if I just go from here, again, going back to a higher thickness, if I actually look more closely and pick a smaller voltage range just here, I would get if I swept in this region, I'd get something that looks kind of like this. It's this kind of rectangle. And this rectangle, usually your current is somewhere around maybe 0, but there's some background current, and that background current is the electrical double layer capacitance, and the current you measure is the charge associated with that electrical double layer capacitance. So to answer the question as to what is the voltage range, you would need to sweep the potential such that there are no Faradaic processes. Additionally, if I swept this potential maybe further, I would get reduction of maybe oxidation of my electrolyte. Maybe I'm past the electrode range. Maybe this goes out here. I can't sweep in this range. This range is really where nothing is happening, and that's where I can learn the most about electrical double layer capacitance. So hopefully that is helpful. And again, I'm sorry if I missed somebody's question in the past about that. Oh, get that guy there. But hopefully that allows you to, or at least to the person who asked this question initially, to hopefully be able to maybe answer or address your question about how. All right, so we have another question, and maybe I can answer it, maybe I cannot. This is from Airtan. I have a question about EIS, electrochemical impedance spectroscopy. How do we understand a target molecule is absorbed on the surface? What is characteristics of absorbance, especially Langmuir type? That's a very good question. And I don't know the answer entirely, but I will hopefully provide you with some information that will help you learn or at least take a give you some ideas about how to know from your EIS data. Okay. All right. So again, we're going to use our favorite tool, PowerPoint. And I'm just going to share this again. Make sure that you all can see it. All right, so I'm going to make this big so everyone can see as much of it as possible. Now, let's think about adsorption on the electrode surface. So if we have an electrode surface here, some kind of conductive metal. Sorry, I can't draw that well. Um, we may have electrical double layer, so maybe I have some charge, some molecules on the surface. I have irreversibly adsorbed species. So I have my double layer here. And of course I have analyte molecules. Just put like an A, they're around. Oops, that's not hmm, delete that. But you at least get the idea. There's some analyte that's around. Some of that analyte, and of course we also have solvent in solution as well, just little guys around here, maybe in the diffuse layer. And then you have some analyte that's perhaps physisorbed or actually fully adsorbed onto the surface. So if I just erase some of these, you may actually have a molecule that's attached to the surface. This is the adsorption that you're talking about. And of course, correct me if I'm wrong when you're talking about this, and you need to give me a little bit more characterization. But usually, when the molecule is adsorbed, you'll have a couple things. The nature of adsorption in and of itself may change the impedance. So one experiment, very very simply, is if I just type a comment, is does does the EIS change with and without adsorption? And more specifically, you can do with and without the analyte at different potentials. So those are kind of some experiments that you can do. You can do EIS at different potentials with and without the analyte. And if you're doing EIS at a Faradaic process, you're going to see this, or you may see more adsorption or a different kind of response. Now, generally speaking, I think that with an EIS plot, the adsorption, you want to think of it maybe from like a circuit diagram. So let me erase, say, half of this so I have some space to think about the circuit. But generally speaking, we have some solution resistance, and then there is resistance associated with charge transfer, and there's also double layer capacitance. And so questions about the adsorption of molecules may actually increase the impedance due to higher resistance. So that's one thing that could happen if you have adsorption on the surface, is the resistance may actually start to increase. You start to have a really big layer of stuff, A, on the surface, and it increases the impedance. That's one thing that can happen. That's possible. And people who do EIS commonly see that when they have stuff stuck onto the molecule, they observe this kind of behavior. Another thing is if this is more conductive and you have spaces that, let's say are not blocked, the nature of the circuit that you use may also change as well. You may actually have a parallel process. So for example, you may actually have another if there are, say, let's say, maybe there's gaps in your adsorbed layer. Well, that's one process, but you may also have another kind of process that's in parallel or in series. So actually, if I delete this, if I move this out of the way, you may actually have a second charge transfer process where you have multiple interfaces in parallel with each other, and maybe there are also some that are in series with one another. So that's another possibility. And of course, it depends on what your system is and what you're looking at. So um, I hope this is kind of helpful. Let me just go back. Say another thing, like there's EIS, but I would also mention that there's EIS, but I also mentioned like techniques like chronoamperometry can be really helpful at learning at doing things like looking at surface coverage of molecules. So that may be another technique, a DC voltammetry technique that Etron you can use to study the surface. It doesn't have to necessarily be purely EIS. All right. So let's see. Oh wait, I just noticed Chris said audio is kind of intermittently and out of sync with video. Am sorry about that, and hopefully um, I'll take a look into. I may not be able to actually answer that or address that right now, but I will look into that. Thank you, Chris, for showing me this. Okay, all right. So another question from Ravi: why solid oxide electrolyzer is good as compared to liquid electrolysis? So Ravi, I don't know, only because I don't know very much about solid oxide electrolyzers. Liquid electrolysis would be, it's a process such as just taking like water with an electrode, platinum electrode, and then generating hydrogen or oxygen from it. I think there may be something. I don't know if there's something about solid oxides that's better, or perhaps maybe the engineering of it. But unfortunately, I don't know enough about solid oxide electrolyzers um, to help you with that. I'm sorry. Let's see. All right. Let's see if the next one from OPA111AM. Alex, in a corrosion experiment, I'm experiencing oscillations due to the high working electrode capacitance. What can I do to fix this? Okay, it's a very good question. Very good question. So I don't know exactly what corrosion experiment you're doing. Some of these are typically things like linear polarization resistance, um, high working electrode capacitance. So commonly, one thing that you may be able to do to address oscillations is change the stability filters on your potentiostat. That may be one reason. So you have a high working electrode capacitance that is changing. Let's see, how do I describe it? It's fundamentally changing the circuit of your electrochemical cell, and your and the potentiostat's ability um, to have an adequate feedback circuit with your for your experiment is being compromised. This has to do with the stability filter on your potentiostat. So OPA 111 AM, I would play around with the stability filter settings. Um, Either going to low or high. Might choose setting it to a low stability filter. So maybe the single kilohertz. And then if that's not working, you may choose a higher stability filter, which should be a setting that's in a higher, maybe tens to hundreds of kilohertz. That may actually be very fast. You may even go to say hundreds of hertz first, and then going to something like higher kilohertz. But stability filter would be the way to go. Hope that was helpful. Okay, so let's see. Some of these I may or may not be able to answer, but I'm going to try to answer as many of them as I can. Guabil, hi, I want to ask, what would be entropy What would be entropy in electrolyte system? What happened with high entropy or low entropy? Thank you. I guess I don't know um, what a high and low entropy electrolyte system would be. Um, Entropy has is always I think of it as the number of available states. And so if more molecules have more available states, and so maybe that's a complex salt in that case. Um, if you have a complex salt electrochemical or electrolyte solution, that would be a high entropy or a low entropy system. But um, I would like to say, and again, I'm kind of making things up. I don't know exactly what would happen, but the electrolyte solution definitely changes things like the uh, electrical double layer capacitance. The electrical double layer is a very complex subject, and its orientation and organization is very complicated depending on who you're talking to. But entropy, what happened? Yeah, so I don't know. I guess like what would be the entropy in an electrolyte system? I don't know exact. Like I couldn't give you like a numerical value for the entropy in a high or a low entropy system. But hopefully, the idea of making electrolyte solutions more complex with more available states, maybe even at higher temperatures, would be ways to increase the entropy. And when you have relatively simple electrolyte systems with not as many complex things going on, you have a lower entropy system. So I hope that is helpful, but I don't know for sure. Okay, and please continue to ask ask questions. Let's see. So, um, Amjet, Amjed, I am making a simple potentiostat using Arduino. For CV, I'm having problems in circuit building with op amps. What would your suggestion? I think maybe your question is a little bit longer. What would be your suggestion? I would need to know a little bit more um, about it. Just saying, for any troubleshooting situation. I don't know exactly what what things are going on. Like, what is the problem? I haven't actually built a potentiostat. I know a lot about the fundamentals of how they're supposed to work, but I haven't actually worked with playing with the circuit itself. But one thing I might just start is a potentiostat. Even though the simplified potentiostat is very relatively simple, I might start with just checking each component of each system. So for example, I might create a with the op amps, I might create a voltage follower circuit. So let me just, I guess, kind of share with you this voltage follower. Let me erase all this stuff first, and also delete this. But in a voltage follower circuit, and make sure that you see the whole thing. Then the voltage follower circuit, so this is your op amp. Okay. One thing I might do for now is so this is a voltage follower, so I have a V in and I have a V out. And in the voltage follower circuit, this is minus and this is positive. This is the inverting input. This is the non-inverting input. I might just make sure that this works first. I might just say if I put plus one volt in, am I getting plus 1 volt out? Just make sure that my op amp is working, and then piece by piece change it so that okay, maybe I add something here. Maybe this goes to my counter. Um, just do some of those things. Make sure you have this simple circuit working as intended before moving on to just plugging everything in as the instructions tell you before going further. Hopefully that is helpful. Let's see. All right, a ton. Thank you so much, Greens from Turkey. Thank you a ton. Which kind of op amps, circuit topology, changing the time constant. Yeah, so Amjed is using this, and unfortunately, I don't know enough. I don't know enough about the specifics of the circuit. I think that's something that I probably need to learn a little bit more about. So again, sorry about that. Let's see. Ravi, if we runs a vehicle on fuel cell technology, can we use atmospheric air as a source of O2? If yes, then does that have an impact on oxygen levels in the environment? That's a very good question. Um, my guess, having not done this before, is that we probably wouldn't be able to use atmospheric oxygen as a source of O2. Now, I could be wrong, but the reason why I say that is I think oxygen in the atmosphere is maybe 20%, maybe 15 to 20% of the oxygen that the air contains oxygen. Actually, I can do a quick, just like Google search, how much oxygen is in the air. And 21%. So 21% of the atmosphere is made up of oxygen, 78% is nitrogen. So that's not a whole lot, especially compared to something like a compressed gas cylinder where it's pure oxygen. And that is going to, so unless you have a compressor, something that's compressing that oxygen and really kind of filtering it in, um, I think that your power output is going to be a big problem for a fuel cell. Um, yeah, I think having oxygen and hydrogen of adequate levels is going to make it difficult. Now, hypothetically, if 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 fuel cell technology was able to do that and it was working fine, what impact would that have on oxygen levels? Um, mm, at least oxygen levels of the environment. Well, actually, I don't know about that either. Um, I don't know if it would necessarily be consuming so much oxygen that it would it would make it super hard to breathe, but that may be an issue as well. But I don't know. Really, the problem is just the amount of oxygen that's in the air. And I think Chris agrees. He actually mentioned that it's like 19-ish% is how much oxygen is in the air, and that's a problem. For it. But that's not to say that we shouldn't work on fuel cell technologies because we're trying to minimize the amount of, say, carbon dioxide and just fossil fuel usage. If you because we can get oxygen, we can get hydrogen. They're somewhat renewable in the sense that we can get access to it, but fossil fuels in and of themselves, you have to drill them from the ground, and we don't have a good way of converting those fossil fuels or converting the byproducts of those fossil fuels back into fossil fuels. So that's still a reason to do fuel cell research, sort of say. All right. Oh, 19, Chris is just mentioning 19 issues where you start having issues breathing normally. Oh, okay. So that's interesting. So if that's the case, if we are taking a lot of atmospheric oxygen uh, out of the air, then there would be a whole lot more breathing issues, is what I would imagine. Okay, I think I tried to get through as many questions as best as I could, and please keep questions coming in. I will be around. In the meantime, there were a few pre-asked questions, and one of them I answered about the electrical double layer. There's another question from one of our tier 2 members. Um, Tarek. And so hopefully his question's pretty complicated, but I do want to try to get into it. And this is only part of the question, but ultimately it's a relatively complex question, and as I wait for some more questions to come in, I can start to address it. So his question: how does a potentiostat ensure a consistent applied potential to the working electrode given a shunt alters the nature of the reference electrode when transitioning to high to mid to low frequencies? So his question, for those of you who are unfamiliar with this part of EIS, is that in some cases when you're doing electrochemical impedance spectroscopy, because you are using a reference electrode such as silver chloride or saturated calomel, you end up running into these high frequency artifacts in your Nyquist plot. You get this kind of bad data, and um, to solve this, we use what's called a reference electrode shunt. And if I share my screen again, and if I take this out, and if I make sure that I am, nope, not me. There we go. So just to kind of let people to know, normally a reference electrode has this kind of construction where you have like a fritted tube. There's a wire, like silver, and then there's silver chloride salt around it, and it's in a solution of, say, 4 molar KCl, saturated KCl. There's a frit here, and this is a normal like AgCl reference electrode, AgCl, and a reference electrode shunt. Now, a reference electrode shunt is when you have another electrode in parallel with this silver chloride, but it's connected to a capacitor followed by, say, a platinum wire. So it's a conductive platinum wire, and this capacitor, maybe let's just say, has like 1 microfarad of capacitance. And so there's these things that happened in EIS where when you have, say, your Z real, and then you have your negative Z imaginary. When you have, and let's just say for argument's sake, just like this is 0, you'll actually start to get some strange like EIS signal that kind of looks like this. You have these like high frequency artifacts. Sometimes it can be negative real impedance, and which also doesn't make sense. And in general, even if that wasn't there, having this kind of little tail in the in the Nyquist plot is problematic. So what we do is we employ this reference electrode shunt, where when we actually, so this is I'm going to use the typing tool for this. It's a little easier to not comment. Box. So this is without shunt. Then down here will be, sorry, I keep hitting comment instead of text box. And this will be like with shunt. And so what you end up getting with this is you don't really get much of that artifact. You actually get more of a normal thing. Maybe this is 0. You actually are measuring a real, again, this is the same like Z imaginary has a big negative sign. And then this is still Z. This is still Z real. Sorry, I just not give myself a lot of space here. Oh, I can actually write below that. Anyway, but anyway, you're able to kind of remove this artifact. Now, granted, maybe I made one small mistake, which is that I have noticed, and I think Neil will attest to this, is that the the EIS plot doesn't look exactly the same. There's something a little different with and without the use of a shunt. So, um, so basically, let me go back, just checking on the chat. Um, so, so there's without shunt and then there's with shunt, and we use this really to correct for this strange high frequency artifacts. And the reason for this mostly has to do with there's an inherent capacitance associated with this kind of reference electrode. We don't know exactly what it is, but I actually think, talking to a colleague, we think it's the glass. So there's charge that can build up on the glass, the edge of the glass of the reference electrode. Use green. So there's charge that can build up on the edge of the glass of the reference electrode, and that can create somewhere between like 7 and 10 picofarads of capacitance. And then on top of that, um, this frit can have a very high impedance, somewhere on the order of maybe 1 to 10 kilo ohms. So 1 to 10 k ohm. So these can be very resistive. And between this low, again, this is like maybe 7 to 10 picofarads, in parallel with this frit, you create what's known as this low pass filter, and it just so happens that this will cause phase delay with the at the high frequencies when you're doing EIS. And so by virtue of having a 1 microfarad, a larger capacitance with a very low resistance platinum wire, the current tends to flow here, at least the little bit of current that's used in a measurement, versus current flowing here at high frequencies. This is the path of least resistance, and it does not cause, or it dramatically minimizes the phase lag associated with the capacitance in this reference electrode. So, with all that being said, on that level of background information, the question is, what does a potentiostat do? And this question, I spoke to a colleague of mine, and we have a couple ideas about what the potentiostat may actually be doing in this kind of situation. So let me make a little bit of space here. Also, before I begin, let me just check to see if there's any. Looks like there are a couple. All right, so there are some. All right, so there's a couple questions. I will get to those questions as soon as I can. All right, but hopefully this is a question Tarek asked a little while ago. So there are these two processes that are occurring, and they're processes that are frequency dependent. And the question really has to do with, what is a potentiostat doing during this time to maintain the potential? So the potentiostat circuit is still the same potentiostat circuit, whether you're in DC voltammetry, whether you're doing AC voltammetry with high or low frequencies. The potentiostat just if I just show you this, there's a reference electrode lead, and then there's a and then there's a working lead, or a working sense lead, and the potentiostat measures the difference between these two and outputs, and this is what we measure. So this is what the P stat measures. Okay, so this part here is connected to this. It's connected to this shunt. Now, there are a couple things to think about or consider in this situation. And the truth of the matter is, it's not, this is complicated. And it's not like electrical engineers know a little bit and electrochemists know a little bit, but I actually think a full and complete picture about what's going on is not very well understood. But what I believe is that at high, like you can think about every frequency of an EIS experiment is a separate experiment. So you're applying a sine wave at 1 megahertz, um, and then it moves to a frequency. It collects all its data points, and then it moves to a frequency of a lower frequency, and then that does another sine wave. And so the EIS data that you take at 1 megahertz is going to go through here, and the reference electrode potential is really based on platinum, like this platinum wire and the platinum redox couple, which might be, this is most likely your H plus two H plus two E minus going to H2 gas. It might be this redox pair. That's what you're actually referencing at the high frequencies, what your redox potential is. You don't have the phase lag, you don't have that phase delay, but this is the potential that the potentiostat is applying with respect to. So when you tell it, I want plus 1 volt, or more specifically, you're oscillating between -10 to say +10. Oops, sorry, let me delete that. You're oscillating between -10 and +10 millivolts with your AC sine wave. That's what you're really applying. That's what the potentiostat is applying, right? That uh, and that's maybe versus, that's centered around 0, right? So there's 0 and it's ±10 millivolts versus of the working electrode versus reference. Well, I think that your reference electrode potential is changing on at platinum, and it's versus this couple. And then when you move to lower and lower frequencies, it's with respect to silver chloride, which means that there can be as much of a 200 millivolt difference in the EIS measurements taken at high frequency versus low frequency. Now, this is something that I just spoke to my colleague about earlier today. Now, sometimes this doesn't matter so much if there's no Faradaic processes, if there's no difference between let me stop sharing. If there's no difference between those between the chemical system at those two potentials, you should still get good EIS data. So, but this should hopefully help Tarek understand a little bit more about what the potentiostat is doing. The potentiostat will always try to maintain the potential that you tell it to and have it apply, but what it's based on and what it's with respect to is complicated. So I hope that's helpful. I think that's mostly Tarek if he asked that question. Okay, so let's keep moving. Ravi, what are the merits of perovskite oxides as the cathode electrode? I don't know. I'm sorry. There are very many. There are a lot of different type of perovskite materials, and I don't know enough about what the cathode materials are and why perovskites are better or worse than other cathode materials. Um, just the nature of just oxides in general, metal oxides. I don't actually know when it comes to an electrochemical system why they are good or better. I think metal oxides are very stable, but I don't actually know. So I'm very sorry about that. Let's see. Suhasutar, what information does the Bode plot give? It's a great question, and I think that's something I can answer relatively easily. And to do that, actually, I can showcase Aftermath software to make it so you don't have to see a terrible drawing. you can actually just see something that looks perhaps more normal. So all I'm going to do, I'm actually going to simulate any circuit. Let's make it interesting. Let's just do this one. Okay, so and let's just look at the Bode plot. So I'm going to try to hopefully blow up the Bode plot, make sure I'm giving this plot a little bit more space. So here we go. This is the Bode plot. So the Bode plot tells you a few things. It's first off, it's a two. I forgot what the name of these types of axes are, but it has two y-axes. It has an impedance magnitude, usually on the left-hand side, and it has a phase angle on the right-hand side. And then the x-axis is is a logarithmic scale of frequency. So during an EIS experiment, you're usually taking data points at say 1 megahertz and then 100 kilohertz. Actually, this would be 100 kilohertz. You know, you have some data points in between because you would typically take maybe 6 to 10 data points per decade, and a decade is this. So there's several data points along here, and then another like maybe 10 or 6 data points along here. And so you can think. So this is physically what the Bode plot gives. It gives you frequency, the real impedance, the impedance magnitude on the left-hand side, and then the phase angle. And it kind of just shows you how the phase angle changes as a function of frequency and how the impedance magnitude changes as a function of frequency. I would say that there's more interpretation. So Bode, I think first and foremost, Bode and Nyquist plots are somewhat interchangeable in the sense that like they both use the same data. Really, like they're like once you know the impedance magnitude and you know the phase angle, you can get the quote x and y components, which is the real and imaginary impedance for all of these, and then you can plot them. So these Nyquist plots are where we can do more interpretation. But I've typically used Bode plots mostly for just kind of thinking about what's happening at specific frequencies, because I can see the frequency information. But your question, very simply, it was just what information does a Bode plot give you, and that's just what it tells you. There's not that much information that's like I don't think too many people. Actually, I take that back. I mean, I think people do look at this to determine some bits of information, but like for example, I was trying to understand the nature of how an RC circuit was working, and I looked at the Bode plot to see like, oh, what is the phase delay? And that the fact that I have phase delay of like 0 at high frequency tells me, oh, maybe I either have a very high capacitance or something like that, and or my resistance is like large, but in this case it's like, oh, my resistance is low. But I don't know enough about interpreting Bode plot data, sort of say. I don't know if that was helpful, or if you were looking for like, oh, what kind of useful information can I get from it? Okay, Sir Haas. So moving on, Ravi, can we use a submarine which works on electrolysis process? Can we use a submarine which works on electrolysis process, H2 fuel? Can we use water from the sea as a source of H2O? Maybe. I think that's an engineering problem because a lot of the research that's done in this type of thing uses very pure water. Seawater has a ton of stuff in it. I'm not just talking about like, it's got salts and minerals and electrolyte. It's got varying pHs. It's got a pH because it has dissolved CO2 in it. It would have to be cleaned up. I think it has to be cleaned up a lot before it can be really used because it can actually damage. There might be a little. I didn't even mention marine life. There's probably some marine life that is that's in the water that could potentially clog or cause problems in the fuel cell. So I think the seawater has to be cleaned up before it's really used as the water source. Um, but I think that's also an engineering thing. I think you could possibly have a submarine that intakes seawater, and within the submarine, it cleans it up and then puts it in as an electrolysis source. So I think hopefully that helps. Um, okay, so I just want to see, Chris, that brings up the question of whether parasitic inductance is an important in these cases. And I think if you had a follow up, you probably have to isolate the shunt with its own op amp to characterize the system. Yes. So Gio, I think that is, so that's very true. Having learned about how potentiostats operate and what they do, and then what we know about EIS and how that operates, it ends up being uh, very, very complicated. It ends up just being a really complex kind of problem because, so for example, when we do EIS, we usually have these 2 points. I can share my screen again, and let me delete all of this stuff here. Okay. And what was I saying? So when we do EIS, we usually have like, let's think my mouse is acting up a little bit. I'm also going to use a slightly thicker here. We usually have like these 2 points, these two nodes, right? When we do circuit fitting of EIS, and we say, oh, we've got this, and then this is a Randall circuit, and then we have a resistor, and that's it. That's we're modeling. This is the system we're modeling. We're modeling the Randall circuit. Well, what is this, right? We call this maybe working. This is the working electrode. But like, what is this, right? The actual circuit may look very different because you have, this is solution resistance between this and the reference electrode. But as we just discussed, the reference electrode, like this may be a sensing point, but the reference electrode has a frit. The reference electrode also has I think, a capacitance, which may be parallel to the frit. What's happening? Oh, sorry, something just happened with my. Sorry, I think my PowerPoint just dropped off. Let me get that back up and running. One second. Let me make sure I share the PowerPoint with you all. This is an important thing. So I showed you the system. We have, oops, eraser. So I showed you this system where you start with a dot and then you have a Randall circuit. I can't draw resistors. And then this is the reference. Well, the reference has frit. It may also have some capacitance now. And then you have some, maybe resistance between that and your counter electrode, but your counter electrode is like that's a thing as well. That probably has some charge transfer resistance, some capacitance, as well as charge transfer resistance. That has a thing going on. This is ref. So like, okay, your potential is here. This is where your potential is applied through between reference and working. And then, but your counter is what's driving current. So your all of your I is coming through here, right? So all of a sudden, like in a 3-electrode system, potential and current are kind of decoupled, and it's not just the value, it's like there's a magnitude and a phase associated with these two values coming from two different sources, all with different components put in. So um, I share that with you because it's kind of complicated. Um, what is happening? Like what what is EIS data actually telling you? Which is kind of rough. Um, okay, all right. So moving forward, let's see. Okay, let's take a look at this question. Kempor, welcome back. If an undivided cell using copper sulfate for the electrolyte solution, a thin platinum wire as the anode, and a large copper plate as the cathode, what will happen when the cell is electrolyzed? So, Kempor, I think I need, let's see. I think that the copper sulfate solution. Well, I think it depends a little bit on the polarization of the platinum wire and the copper plate. And if I didn't know better, I would say there's a good chance you're going to start coating platinum, or sorry, you'll start coating some copper onto your onto your onto your platinum wire. If copper just by itself is in like it oxidizes. I'm thinking if you were to now if you had this say at like open circuit, I think that the copper might start depositing on your platinum electrode, but you would need to it's got a positive potential. If you're applying more positive potential, you're not reducing the copper onto the platinum. But you would have to look at the potential difference between those two. I think that copper sulfate it might also deposit on the platinum, or sorry, on the copper as well. But I think it depends. I would need to know a little bit about the polarization of how you're polarizing these two and to what degree. So if the platinum is the anode, which is oxidizing, the copper is reducing. Well, I think actually, as I think about this a little bit more, assuming I don't know very much about the magnitude, I think you're going to start to reduce copper ions, from the dissolved solution onto the copper plate. That's what my guess is. My initial guess. If you have platinum as the anode and copper as the cathode. Just an initial guess. I hope that's helpful. Okay. Let me see. What's this last comment from George? Or sorry, Chris. Georgie. Sounds like very inefficient plating cell. Yes. um, Watermark membrane, then DIV resin process. Steam process. I don't remember, George, what this is with respect to who's maybe that's Kempor for maybe that's Kempor's system. Let's see. You're saying, but does disproportionate size of anode versus cathode have any effect? Mm, yes and no. So to a degree, I would say that um, like if this is hooked up to a potentiostat, um, could you run into like a compliance voltage issue with plating? And to a degree, right? Like if platinum is oxidizing water into oxygen on one side, then that water goes away and it's going to keep doing it. Um, the current, so the rate at with which this process happens, will play a role. The rate of the reaction will play a role, but whether it happens is based on thermodynamics and to a degree, yeah. That's mostly based, I would say, on the thermodynamics of the system. But yeah, the size I think would affect mostly the rate of the reaction, especially if you have a very big plate. You're going to limit how much current and how much plating is going to happen. Oh, so he was okay. Yeah, he was talking about the O2 oxygen from here. So the hydrogen oxygen from seawater, if you used a water marker membrane. Oh, okay. Yeah, yeah. So that would be a way of a submarine converting seawater into useful DI water that could be used in a fuel cell. That's a very good point, Chris. Very, very good. Okay, so hopefully this has been helpful. I don't doesn't look like there are any further questions. I'll wait a little bit longer in case a question comes up. But and if you just have any comments, that you want to talk about or just anything that's going on, please let me know. For those who are interested or curious, last week um, Neil was traveling. He's still traveling now. He's actually on vacation, much needed and well deserved break. Um, and then I was doing this electrochemistry boot camp, helping to teach it at UNC Chapel Hill. So Pine Research is located in Durham, North Carolina. We're very close to UNC Chapel Hill, and we get a bunch of students together to run through some electrochemistry experiments. And that was a lot of fun. I always have a good time teaching people about things like IR compensation, how potentiostats work, and troubleshooting electrochemistry problems. So we were both out last week, which is why we didn't have the live stream at that point. Um, I also do need to understand or figure out whether Restream is producing, um, based on earlier comments. I think, what was it? Let's see. Yeah, Chris mentioned that the video is out of sync, so I'll need to look at that if that's the case, which is very unfortunate. Let's see. Chris has another comment. It really depends on current density and over potentials. What side effects you'll have to someone? Yeah. That's right. So, current density and over potential, and any side effects when you're doing a kind of a plating experiment um, for the copper plate and the and a thin platinum wire. Yeah, so next week we're hoping to still Neil will be back, and we'll hope to do more live streams and answer any electrochemistry questions you guys may have. Stay tuned to the YouTube channel. We're still figuring out what live stream or streaming service we want to use. Zoom has worked well for us in the past, but recently it's been a little problematic, and I'm kind of enjoying using these kind of new streaming tools that are very powerful. So but we'll see how it goes. So please again ask any questions, and I'll try to answer. Let's see. Of course, I might not know. In the case of supercapacitor, this is from Muhammad Azim. In the case of supercapacitor, what will be the ideal value of current density and energy density in literature review? I do not know because I haven't read the supercapacitor literature, but I'm pretty sure, Muhammad, you can find a review article on supercapacitors. And let's see if I can't just do a quick Google search. Um, Capacitor review article. And this way, um, interesting. The NIH, National Institute of Health, looks like they have a review on supercapacitors. Yeah, so they review several types of supercapacitors. One's based on electrical double layer capacitance, pseudocapacitors, and hybrid supercapacitors. Um, I'm trying to see whether or not I'm actually skimming through an article right now to see whether or not they give information about um, density. Most of the time, yeah. So some of these, let's see, one of them single-walled carbon nanotubes, specific capacitance of 1 amp per gram, and then they also report 76 milliamp hours per gram. So they also will report it by, I guess, energy density in that case. So would there be an ideal value? I don't know if there would be an ideal value. Let's see. Some fabricated. It looks like depending on what type of supercapacitor, the values will be very, very different. But I've seen some of these are kind of small, like several watts per kilogram, like 47 watts per kilogram as energy density. Some are 400 watt hours per kilogram. And then, of course, the number of cycles that it does is another thing. But you're talking about energy density. Some also report it as capacitance, so specific capacitance as a way of looking at it. But I think it really depends a lot on the specific type of supercapacitor that you are looking at, because if it's made out of different materials, if it's let's see, oh, pseudo capacitors. All right, so pseudo capacitors. Thank you for that clarification. I don't know. Let's see, pseudo capacitor. Let's see. Pseudo capacitors. Let's see. So it looks like pseudocapac. No, trying to figure out. Okay, so it looks like pseudocapacitance is based somewhat on some intercalation under potential deposition pseudocapacitor, redox supercapacitor. Um, some are based on ruthenium oxide. Just kind of keeping an eye out for different ones. But what I can do, just so that you know what I'm looking at, is I can type in. This is literally the article I just typed in to figure out what it is. So maybe that'll be very helpful, Mohammed, as you try to determine um, what's an ideal value for current density. And I bet the size and geometry and its construction will play a big role. So you may have to do some averaging of that. But I hope that article from the NIH at least is helpful. But yeah, I would look at some review articles and then find the specific one. Like ruthenium oxide seems to be a type of, I think that was ruthenium oxide, appears to be a certain type of pseudocapacitor. Um, and its energy density will be very different than, say, capacitors based on carbon nanowalls, carbon nanotubes. Sorry. Okay, so we have a question from Adarsh. What is the typical amplitude used in EIS, and how high can you go? This is a very good question. So the typical, I will get. Okay. Yeah. So let me answer this one first before I get to Mohammed's next question. So typically, the default. So first off, There's two types of EIS. There's galvanostatic and there's potentiostatic. I would typically say that for potentiostatic EIS, you want to use an amplitude around 10 millivolts, um, and that's maybe peak to peak. They also have was it square? I'm trying to think what's the just like figuring out how we describe it. Root mean square. So there's root mean square, and there's peak to peak, and then it's just peak. Um, but yeah, 10 millivolts. So it's usually relatively small. And the idea, of course, behind EIS is that you're able to perturb the system enough that it elicits a response, but not so much of a response that you're doing a lot of chemistry to it and the system is no longer stable or linear, or kind of fits the kind of Kramers-Kronig definitions of valid EIS. Now, if you're doing something like galvanostatic mode and you say have a very high impedance, you may need to use something like milliamps of current. It depends again on the system, but hopefully 10 millivolts is kind of the typical one for potentiostatic. And then you may decide to go to something like milliamps for a galvanostatic EIS experiment, um, if you have a system with high impedance. Or no, is it high impedance or low impedance? I think that's low impedance. I think that's low impedance. Uh, let's do some. I'm just gonna do some V equals IR. Let's see. So if I just do, let's say V equals IR. So if I have so if if the impedance is very low, I might need to have I may need to have a higher, or actually even a lower. I may need to have a high current for a low impedance, so that the voltage that's measured on the potentiostat is better. So that's kind of the thing. So Adarsh, I hope that was helpful. But 10 millivolts per 10 millivolts peak to peak is not a bad not a bad way to go. So hopefully that's helpful, and please let me know if you have further questions on that. All right, this is following up with Muhammad. What is the main difference between EAS, GCD, and term retention rate? I don't know. Every time, like, I've seen GCD, but I'm not. I think it's a common term used mostly for. Yeah, galvanostatic charge discharge. I think that's it. So I think that's what it is. So, electrochemical impedance spectroscopy is an alternating current or voltage technique to kind of probe the the kind of what we think of as the circuit system. It's kind of a non-invasive technique to probe the things like the capacitance and the resistance, and maybe even some useful electrochemical properties of like a battery. Charge, I think galvanostatic charge discharge has to do with charging and discharging a battery, and then determining how long that lasts, or it measures the stability of the battery. It's a totally different technique. Galvanostatic charge discharge is like, I'm charging the battery, I'm discharging the battery, charging the battery, discharging the battery. EIS is applying a sinusoidal potential or current, measuring a corresponding potential or current out, and then measuring the ratio of those two, to learn more about, I would say, the inner workings of that system. I don't know, actually. I haven't heard the term retention rate before, so I don't think I could answer that. I don't think I could answer that well. I don't think I'd be able to give you a good answer of what is the retention rate, or what's the difference between like retention rate when it comes to, say, batteries or something like that. But Muhammad, I hope that's helpful. Chris says sawtooth, and Chris, thanks for hanging out. Okay, let's see. Let's see. All right, Kempor, will your company's potentiostat software work with DIY potentiostat like Juami potentiostat? Why or why not? So the answer is no. We won't. It doesn't, and that's simply because of just the way the software was programmed. We don't take just kind of random inputs from different potentiostats. Our potentiostat software is designed to specifically work with the potentiostats that we've created, and there's a lot of electrical engineering and testing, software engineering and testing that goes into designing and building our potentiostats. So I'm sorry that ours can't just work with it, but even other companies' potentiostat software won't just automatically work or recognize another potentiostat. So that's I think one of the big issues is that potentiostat software is designed um, to notice another potentiostat, and if that's not programmed in, then it won't actually detect it. So, Kempor, I hope that answers your question. All right, let's see. We have a question from Alex Wang, and uh, electrochemical oxidation of ethanol to acetic acid. I think is it possible? So let me see. Um, I don't know. This is definitely a. I think it probably is, but I don't know the answer to it because I'm not an organic synthetic chemist. But yeah, I think I would have to look into it in a little bit more detail. I'm just thinking about the structure, and I guess as I wait for like more questions, I can take a look. So this is ethanol, and then I believe acetic acid is this, right? Or actually, oh no, there's no H here, so that's ethanol. Yeah, no, formic acid has one carbon. Acetic acid has a carboxylic acid. I forgot. I'm forgetting all of my. Yeah, I'm forgetting all of my electric. Oh wait, no. There's a bond here. Oh yeah, wait. Here we go. Yeah, I think this is acetic acid. You need another oxygen. So could you do something? Yeah. So I think this is acetic acid, and then you need to do something to this. You need to oxidize that in the presence of something. I honestly don't do enough uh, organic chemistry to know or think about that process. So, I accidentally wrote an acetaldehyde. Um, let's see. Oh, and the Darsh is also saying yes, it's possible to oxidize acetic acid. I did some work on that. That's acetaldehyde. Yeah, thanks. I have not. I'm sorry, I haven't done that much work on on electrosynthesis, and it's been I think well over a decade since I've done organic chemistry. Sorry. Okay. All right. So that's it. Okay. So this is another. Is there any potentiostat software that you know that will work with just about any potentiostat? So I would say no. I mean, you can probably talk to other potentiostat companies, but generally speaking, uh, I think that there's just a lot of like it's a firmware thing. It's like how does the software know that this is a potentiostat? Like something has to be programmed into it. There's definitely a lot of software that allows you to use, I want to say, other like that might be able to talk to MATLAB, for example. So if you programmed your potentiostat in MATLAB, then you might be able to get that to work with um some other software, some other potentiostat software. But at that point you're kind of interfacing multiple softwares talking to each other, and I don't think that there's any potentiostat software that'll just work with any potentiostat universally. All the potentiostat companies, we don't talk to each other about this kind of stuff. So I'm sorry, Kempor. Let's see. Okay, some talking, Alex. I'm glad that you're able to talk to Adarsh about reduction at the cathode. Okay, let's see. Adash, what is the typical amplitude used in EIS and how high can you go for studying electrocatalytic reactions? How do you decide the DC polarization in EIS, onset or peak potential? That's good. This is a really good question. So let me, I'm going to again share. So I'm going to share this again. So a couple things to think about and note is if you have like a cyclic let me use a thicker pen. So if I have a cyclic voltammogram, and let's just do this. Okay. Okay. So I have potential, got current. Now, part of the requirements for EIS is that, and I'm gonna maximize the this so you can see it. So what you're trying to figure out is at what potential do I do EIS at? Do I do it here? 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 All right. These are all questions like what, sorry, that's not a very good straight line. What potential do I polarize the electrode at? Well, there are a couple things. So one is very obvious. Now I know you're doing electrocatalysis, and maybe for electrocatalysis, that's happening here. So maybe this is where your catalysis is happening. And then, but maybe here, like nothing's happening, right? Nothing. Well, what you kind of want to do, so the cyclic voltammogram is both good and bad at this, but you want to think about zooming in on segments of your voltammogram and figuring out what does this look like? Do I get a linear, kind of a straight line or a linear fit if I sweep the potential back and forth in this small section? So if I blow that up, it's like, well, that just looks like this. If I move the voltage between these 2 points, I'm still linear. I'm in a non-Faradaic region, and I'm going to get a EIS, I'm going to get a Nyquist plot associated with this. And I can probably apply a pretty big voltage range while still, sorry, I'm just making this big. I can probably get a pretty big voltage range that I can apply, a big EIS amplitude if I'm in this range. But if I'm here doing catalysis, and this is kind of strange, but like if I took a big voltage range like here, well, if I blew this up, it looks kind of like this. This is not linear, so not linear. So I can't apply a voltage at this DC offset. Let's call it E2 and this E1. I can't apply a very large voltage range at this DC offset because it's no longer linear. My EIS data would look super strange. But maybe I could zoom in on this region. And here, maybe this does look kind of linear. So you need to ask yourself the question, like, is it linear? Is it stable? And maybe I can get away with applying a higher voltage and getting more current out. And I kind of need to get more current, right? As because the impedance, just V equals IR and or Ohm's law. And I have this, right? When these numbers are big, I can very easily measure the resistance or the impedance. But when some of these are small, it's hard for a potentiostat to measure those accurately. So it's nice if I'm able to apply a large voltage here, and then I get an adequate amount of current in this non-Faradaic region. Maybe I have to do that because the current's very low here. But here, when I'm doing catalysis, the current's super high. I might have to apply a very small amount of uh, sinusoidal potential to actually get a linear response and sufficient, good quality data that's stable. It's not changing a lot, and I'm still able to probe the catalysis. So doing a DC offset here for EIS and doing one here will give you, basically, it should give you two different EIS spectra. So hopefully, Adarsh, this should hopefully answer your question. I hope. Um, okay. All right. So let's see. Going through this, I'm gonna try to let's see. Alpken Aras. Hello, glad I could catch up. I am taking an electrocatalysis lecture and I never understand why there is potential drop in metal surface and how it increases again in the electrolyte bulk. Okay. So that's a great question. So there are a couple things to think about for electrocatalysis when it comes to potential drops. So one of the depending on who is teaching the course and what they're going on, every time you have an interface, you're going to get a potential drop. You can think of it as the electric field has a certain strength, and when it moves from point A to point B, and it's between two separated things, it may drop off. So let me, I'm actually going to try to use this lasso tool and let me share my screen again. Hope this is helpful. So, oops, I'm going to get this to 4. So if I have this is my conductive metal surface. Okay. So your professor may have mentioned that there's a potential drop immediately across the working electrode surface. What they might be referring to is the drop associated with the electrical double layer. So the interface between the metal and solution or solvent and stuff like that. And there's some charge in here. There's like plus, there's minus, there probably won't be a plus if this is negatively charged, but this is mostly like minus charges, solvent where there's nothing. And so there is, when the potential is applied, you apply, say, some voltage, and it's at a level, it drops off across this interface of the electrical double layer. So the actual so it's strange, the actual potential is that's being applied here at this point in solution. So if this is distance, right, the potential at this point that the molecule feels is lower than the voltage at the working electrode. Okay. Now the other and I think let me just drop this so that you can see, like I said, distance back here. Again, let me make this big. So the other type of potential drop has to do with solution resistance. So it's this bulk resistance in the solution. And it's easiest to think about this using a circuit diagram. Okay, so let me delete this and show you. I did. So if you have your working electrode, which is your conductive metal, and then you have, this is your double layer capacitance, your electrical double layer capacitance. You have charge transfer resistance. And then you have what's known as bulk solution resistance. This is what's known as, I'm going to type this because it's a little bit better. Uncompensated solution resistance. Okay. And basically, and then you have, say, your working electrode, or sorry, your reference electrode here. This is where the reference electrode measures the potential. So you can kind of see actually very clearly from this, there's two places. Like if I apply plus 1 volt across the working and reference electrode, there is a drop off here. There's a value here, and there's a value here. Like, and both of these need to add together to get 1 volt when I'm doing an electrochemistry experiment. So this solution resistance, some Ru resistance, times the current that flows through the cell gives me what's known as my IR drop. And if you are doing electrocatalysis and you are studying this process here, this becomes very problematic because you think you're applying plus 1 volt to your system, to your electrical system, your electrocatalytic system, but really you're applying less than 1 volt. And this leads to a lot of inaccuracies. So especially in electrocatalysis, when you have a lot of current, so when this gets big, that's a problem. If you have a large area and there's a lot of solution resistance, this becomes a problem. And so you can see huge changes. I ran this kind of demonstration in at the CV bootcamp I did last week. But if you had 1 milliamp of current and 300 ohms of solution resistance, that equates to 0.3 volts, which means what you're applying to the working electrode interface, which is what you care about, is 0.7 volts. And if you told the potentiostat apply 1 volt, but only 0.7 is getting applied, that's a big problem. Like that's a huge inaccuracy. And if you have more current passing, like if this is 2, then you have even less applied voltage to your working electrode interface. So I hope this kind of clears things up a little bit with regard to understanding the voltage drop and how there's a drop across the working electrode interface and then a drop across the solution, the bulk solution resistance. Okay. Yes, and so you also said you guys mentioned EDL. Yep. So hopefully that is covered as well. I'm going to try to go through others. Sergo, what do you think is the future of electrochemistry? That's a great question, and I could probably spend a bunch of time. So the future of electrochemistry. I think right now there's a lot of research in batteries. That's mostly what a lot of people are spending their time doing. There's a lot of stuff in nano electrochemistry. People are doing understanding smaller and smaller and more fundamental things. Electrochemistry at this point is really a tool. It's really just a type of science that we use to solve problems. And so batteries, fuel cells, I think mostly batteries are going to be is really going to be the future of electrochemistry. And I say future at least within the next 5 years. I mean, they're already super important. And electric cars as well, EV and photovoltaics and all those things. Electric vehicles are it's big, and additionally, there's another component which is solid state electrochemistry, which is something I'm not as familiar with, and I wish I was. But if you're in the electronics industry and you're making, silicon wafers and all that kind of stuff, like there's a big electrochemistry component in the semiconductor industry. So that is that's kind of the now, I would say, maybe not even the future, but it's a huge. There's going to be a lot of money and investments going into that. But I would say batteries, electric vehicles, and a lot of companies are going deeper and deeper into that kind of stuff. So I hope that answers your question. That's just a purely opinion piece. But thanks for asking. Let's see. So Tamal is asked how to calculate VBM from LSV. What I know LSV is linear sweeping voltammetry, or linear sweep voltammetry. I don't know what VBM is. I mean, maybe I know it. I'm unused to the acronym. So Tamal, if you could ask, if you could just tell me what that is, I might be able to answer your question or provide you with um, some support, or maybe I may not. I might not be able to. Let's see. Kempor, is it possible to build a completely software-based potentiostat? Why or why not? I think the question in that case is, what is a software-based potentiostat? um, so you mean a potentiostat that just uses a computer to run? I think maybe is that your question. If that's the case, I would say that the answer is no, because now I'll tell you a couple. So I'll mention a few things. First off, um, potentiostats naturally use analog software, or not analog software, analog components. You're looking at potential, you're looking at current. These are very real things in the physical world. Batteries, corrosion, redox properties, they're all physical, real things. And there's nothing in a computer per se that that interacts with the real world in that way that that doesn't require some excess electronics. Like computers have power, but I don't think computers, I mean, I could very well be wrong, use operational amplifiers as components. I may be very wrong with that. There's a whole series of electronics that that are used in things that aren't like computers per se. But yeah, I don't think just programming. I don't think you can just program a computer with some software and then have it do electrochemistry, because there's just a lot of circuitry that goes into a potentiostat that just doesn't exist in a computer, at least to my knowledge. Now you can build software that can simulate electrochemical experiments, and we have it, and but that's not doing an electrochemistry experiment outside. So that's I hope that answers your question. It's really a, I don't think there's these high gain operational amplifiers pushing volts and amps of power through it in a computer that can be easily used to put into an electrochemical cell. I could be wrong, but that's at least my knowledge. All that being said, it'd be really cool if we could do something like that. All right. So Chris commented, metal interface potential. Is there a significant effect related to charge mobility at the surface of the lattice? Oh, well, probably. At the surface of the lattice. Yeah, but I think charge mobility, again, it depends on the metal. Most electrochemistry is done with very highly conductive metals like glassy carbon. Well, not like glassy carbon is a conductive material, but like platinum and gold, very conductive. It's very easy for charge to move around. Charge usually takes the form of ions in solution. So I want to say that mobility, or charge mobility, is very much related to like the electrical double layer and the electrolyte solution. But that's just my metal interfacial potential. Yeah, this is just kind of some of my thoughts about it. And uh, let's see. A particularly elegant way to get a Kelvin connection at the surfaces. Yeah, yeah, that's right. There's the working sense and the reference electrode are basically probes on a multimeter that you're connecting to an electrical cell, an electrochemical cell. So to really understand the surface, like you inherently just have these things in it, and there's really not much of a physical way of connecting these two. But it's that's part of the, you want to get these two things connected, but there is no elegant way of connecting those things to the surface. Yeah. So yeah, you're right. You're always gonna have some solution in the way. Uh, I never thought about it like that. Thank you. You're very welcome. I hope that was helpful. Let's see. I'm just kind of going through these biorelated oh yeah, that's regarding the future of electrochemistry. So I do think that there's a lot of people doing some bio related electrochemistry, but I also think that it's very far off. Like some people have been trying to do like maybe some people are studying cells, you know. There is an aspect of electrochemistry for studying neuroscience, right? Like dopamine is an electrochemically active um uh molecule. It's an electrochemically active molecule, but it's also a neurotransmitter. And so detecting other neurotransmitters can be used, but that's in the neuroscience side. But yeah, there's electric like Tylenol, acetaminophen's electrochemically active. I don't think it's used in for electrochemistry stuff, or they don't. It doesn't have medicinal properties that are necessary to the electrochemistry. But yeah, sensor development for bio stuff is big. There's a lot of people trying to make biosensors. I just don't know how, like, glucose detectors are the only big commercial electrochemical sensor that really exists, to my knowledge. Of course, there's things that can detect trace metal ions and stuff like that that uses electrochemistry, but yeah, I still feel like bioelectrochemistry has a long ways to go. That's part of the future. Um, just kind of going through. Do you think that if we understand catalysis steps of water so well, we can build water-powered vehicles and stuff? Somehow, I have a feeling hmm, of this. Somehow, I have a feeling of this since we have around some energy release there. Yeah, so water itself, so a fuel cell operates by taking hydrogen and oxygen and then forming water. It forms water and releases energy, and that's the energy that we use. Water itself won't power a vehicle, but water can, because water uh, doesn't have stored energy via chemical bonds. It's hydrogen and oxygen forming water that releases energy. Um, we have a lot of understanding of it. It's just a matter of there's the energy output of these hydrogen fuel cells, and then really making it. Um, there's a cost, and then there's an energy output, and we may understand processes really, really well. Or I would say, so we think we understand them very well. There always seems to be more and more questions about it. But can you design catalysts that are really good and really efficient for it, even with such a good understanding? That's also viable for commercial applications. Let's see. So, Chris, even with the signal conditioning power line issues, current analog modes. Yeah. So this is I think it's related to software controlled potentiostats. purely software controlled potentiostats, I don't think. Yeah, there's just analog components that are required for doing that kind of stuff. Um, let's see. Just moving through. Uh, Creativity 1713. When I do IR compensation manually to LSV, the LSV sometimes shows bending curves, though I lower compensation ratio to 80%. Compensation was conducted by EIS. Is there any solution to solve this problem? Um, so a a bending curve. So let me I may actually have, let's see, do I have data on this? I don't think I have the let me go. So I might be able to answer this question a little bit by going to our website, talking about IR drop, and seeing whether or not um, I can answer your question. So I'm gonna go to. I'm gonna share. Hold on. Oops. Oh, okay. Okay, so I'm gonna keep it like this for now. So I'm gonna move this out of the way. Just your question. But when you say that you see bending, I'm assuming that you're seeing this kind of action, creativity, where normally you have a voltammeter where the slope here is nice and pretty high, pretty steep, but normally you're seeing this kind of bending like this. Please let me know if that is what you say. Um, so if you're getting something like this and you're seeing bending, or you're still seeing this even with IR compensation, and actually maybe I need to use. I don't think I'm actually. You can actually see what I'm pointing to. So if you see this bending here versus this straightness, this bending still has to do with a level of uncompensation. So you might not be compensating adequately enough. And remember, with IR drop, as the current increases, if there is an uncompensated component to it, the solution resistance is still it's going to lag the current, which is why you're getting this kind of elongation of the of your cyclic voltammogram of your duct. So you have it at 80%. You may have to increase it so that it's compensating more, for this increase if you're seeing that kind of behavior. And using EIS to determine the solution resistance is perfectly fine. You can also, it's probably the best way right now to do it. There are other techniques you can use. You can use current interrupt, positive feedback, or potential step. Those are other techniques you can do to confirm the value of the solution resistance. But the elongation of this means that you have some resistance, and you're also probably drawing a fair bit of current. So you have this steepness, sort of say. So I hope that is helpful and answers your question. And creativity, please comment if you need some further elaboration on this. Okay, let's see. Adarsh, post IR compensation, is it less reliable? Is it okay to do it in case it's not possible by potentiostat? So yes, so you can do post IR compensation only for the voltage, only for determining accurate what an accurate voltage is for the peak positions, but it is not sufficient in determining, for in terms of its current measurement. So when you apply IR compensation, you will get more current because the potentiostat, to compensate, the potentiostat applies a higher current to the electrochemical system. And so the current with a higher potential also goes up. So potentials, you can extract some value via post processing, but the current you cannot. Um, and some people also argue to a degree like you're not actually applying a linear sweep without adequate compensation. But yeah, if you just need the potentials, like then post processing is fine. Hopefully that's helpful. Um, so Tamal, I'm not so sure what CBM is. If you could tell me what I know LSV, but I don't know CBM. If you can tell me what these acronyms mean, I might be able to help with answering your question. Sorry about that. Okay, Kempor. Is there a manual way to maintain a low voltage with a high current level in an electrochemical cell? Something that may have been done before a potentiostat was invented. Oh, um, I I uh, I honestly don't know. I think you can have there are probably some electrical circuits out there that yeah, there probably are some circuits out there that can do it. The potentiostat circuit really is about maintaining the potential that you tell it to. So even as things fluctuate in your system, your potentiostat is saying, "Hey, make the potential between the working and the reference these two things, or make it one thing." It's just this one value. But a low voltage with a high current level in an electrochemical cell. Well, one thing you could do is if you um, I honestly don't know, Kempor. I may ask my electrical engineer a little bit about that. But the potentiostat circuit is just about keeping the potential the same. Um, to get um, all of these, like, you can get a low voltage and then perhaps you can amplify the current in some way, but there's a lot of analog electronics that I just don't know about. All of this requires some level of um, amplification. Let's see. Chris is actually saying um, a very basic power supply should be able to manage it. Even a variac rectifier would work. That's true. I just don't know what the voltage, like, to maintain the low voltage requirement and high current requirement. That's what I don't know. Um, and again, to to have it maintain that voltage, I also don't know. But you could do some work on that. If you're only applying like a static level, it might work. But yeah, Chris, that's a very good point. Um, yeah. So yes, he's interested in actual potential, and says that's very helpful. Very good. Okay, I'm glad that this is very very helpful, and you're all able to get some good answers here. So I think with that said, we've been live for a little over almost a little over 2 hours, even with the feed, and I think that's a good amount of kind of questions right now. So I hope that this was all very helpful. Again, maybe early next week I'll have the live stream information. The YouTube video will be up with description and questions available for you all to watch and listen to later. All right. I hope you enjoy this. I hope you all have a great weekend or week or wherever you are. And take care and keep us in mind or stay tuned to Pine Research on our Twitter and YouTube for further updates and things like that. Please reach out to us with any questions in the comments. All right. Take it easy.